Washington State University. Go Cougs!
Welcome back to the course on behavior analysis from ambient sensor data. In this segment of the course, we are discussing activity learning techniques, and in this module, specifically looking at activity recognition. In the previous video, we talked about how to extract features from a window of sensor data that is collected while a resident performs normal daily activities. In this video, we will look at how to map that feature vector onto a label that indicates the activity that the resident is performing at the time. We previously showed a video in which a resident entered a home filled with ambient sensors and performed a sequence of activities. The collected sensor data was displayed in the upper left, and our task for activity recognition is now to map that sensor data onto a label indicating what the resident is doing. In this case, entering the home, followed by putting away groceries, or another of the activity choices we have available. In the previous video, we talked about how to define a window or a subsequence of the sensory events collected by ambient sensors in the home. Now, given the feature vector extracted from that window, we are mapping this feature vector onto an activity label. In our example, a particular window could represent the first 10 sensor events in the sequence collected during our demo. And on the left, we are looking at the corresponding feature vector, which we will refer to by the variable v. Activity recognition then maps a feature vector, such as v, onto an activity from a set A of possible activity classes or activity labels. When we perform activity recognition or write a program to automatically perform activity recognition, we have a set of possible activities to choose from. What we often work with are activities of daily living, and we have a set of very common activities here that includes enter or leave home, sleep, bed toilet transition, relax, work, cook, eat, wash dishes, housekeeping, laundry, putting away groceries, and notice that we also have a catch-all activity class that we will refer to as other. This way, we ensure that every sequence has the corresponding activity level, a corresponding activity label, either predefined or this other category. The activity recognition algorithm then maps the vector v onto a choice of activities from this set A of possibilities. In the case of our first window here, consisting of the first 10 events and represented by a feature vector v1, we would likely map the feature vector onto the activity enter home. As you can see, not only is the resident opening the door and moving around the entryway, but from our feature vector, we might also know that the home has been empty for a while. This could be indicated, for example, by the sensor elapsed time feature that we discussed in the previous module. And if it had a large value for front door, that would indicate that the door has not been accessed for a while, possibly indicating that the resident has not been home for a while. Another one of the windows highlighted by the blue box here and shown by the feature vector v2 may be mapped onto the activity put away groceries. Some of the other windows may not be so easy to discern. This box here and the corresponding sensor events might indicate putting away groceries, but there is an entrance into the living room at the end, which is a little bit inconsistent with that activity as a whole. There are several steps involved in performing activity recognition, some of which we talked about in earlier modules. First, we collect data from sensors. In this particular course, we're talking about ambient sensors, such as the motion sensors that were described earlier in this course, and comprise the sensor data that we are analyzing in our example, along with door sensors. The activity recognition process is somewhat sensor agnostic, in that it would be similar if our sensors are not ambient, but instead are wearable sensors such as accelerometers, data-rich sensors such as microphones or video, or sensors placed on objects such as RFID or pressure sensors. Once the data is collected, the next step is to pre-process the data to possibly filter out or clean noise, to handle missing data, and to segment the sequence into subsequences or windows of events. As we discussed in the previous video on feature extraction, we either have to define a fixed size window from which we will extract features, or apply segmentation in order to divide the sensor stream into individual segments, each of which corresponds to a single activity. Once the data is cleaned and broken into individual windows, we then extract a vector of features like we described in the previous video. Finally, we can apply almost any of the well-known machine learning-based supervised learning algorithms or classifiers to learn a mapping from the feature vector to an activity label. In the literature, there are many activity recognition classifiers that have been used for activity recognition, and most of these classifiers are also available as Python libraries. These include naive Bayes, decision tree or a forest of decision trees, a support vector machine, probabilistic graph models like hidden Markov models and conditional random fields, Gaussian mixture models, neural networks, stacked autoencoders, or ensembles of classifiers. While any classifier can be used and no single classifier always performs best, there are challenges that occur in activity recognition from sensor data that are not always found in other machine learning problems, so we need to discuss them here. First, there's typically a very skewed distribution of data points among the available activity classes. For example, this graph shows one particular data set collected using ambient sensors in smart homes. From this set, we can see that the number of data points that appear in the predefined activity categories, including bathe, bed, toilet transition, cook, eat, enter and leave home, hygiene, relax, sleep, take medication, and other, are not evenly distributed. Because there are so many varied activities that people perform outside of these defined categories, many of the actual data tends to fall into the other category, making it a much larger set than the others, than the predefined categories. And even among the predefined activity categories, there's a fairly uneven distribution. This creates problems in several ways. For some activities that do not occur very often, such as bed toilet transition, enter home, and leave home, there may be an insufficient number of data points to properly train models that can recognize those activities with high accuracy. Another problem is that with such a skewed class distribution, classifiers that are attempting to optimize recognition accuracy will tend to put many of these data points into the majority class, such as the other class in this case. Individuals who want to use activity recognition algorithms have to find ways to address this problem. Sampling techniques can be applied here to replicate or generate artificial examples similar to existing points in the smaller classes, and that's called oversampling. Or they may actually remove some of the data points from the larger class, and this is called undersampling. Alternatively, we can try to break the larger classes into subclasses in order to make the distribution more uniform. Another problem is that the data points are not IID. They are not independently and identically distributed. As we discussed in the previous video, each data point or feature vector is not independent of the data that comes before it. This is particularly true if we allow the windows to overlap, as we see in this case. If we extract features from one window and then move the window forward by one sensory event and extract a new set of features, most of the windows will have the same information in common. As a result, the individual data points corresponding to these separate windows are not independent of each other. Even if we move the windows farther apart, as long as they overlap, there's going to be some commonality between the windows. One implication is that we may introduce bias when we test our ability to recognize activities. In this example, we have moved each window forward by one sensor event. If we are going to test our machine learning algorithm and its ability to recognize these activities, we might randomly select 2/3 of the data points to learn activity models, and the remaining 1/3 of the data points to test the model. For example, here we might choose to use the red labeled vectors for training and the green labeled vectors for testing. But we can see that there is shared information between the training vectors and the testing vectors, or between the training windows and the testing windows. In fact, the feature vector v2, which is used for training, and the vector v3, which is used for testing, have 9 out of the 10 sensor events in common. One possible solution to this problem is to ensure that the windows used for training and those used for testing are far removed in time. In this case, we might consider using all of the feature vectors v1 through v6 for training, and then use the feature vector at the end, such as v21, for testing. Of course, there are additional challenges, and one is introduced with the testing method we just suggested, namely concept drift. An individual does not tend to stick to a single routine permanently. As seasons change, there's a job change or family change, the person's schedule and method of performing activities will change as well. When this happens, our suggested method of training a machine learning model from data early in the data set and testing it from data later on may actually result in poor performance of the learned model because of drifts or changes in the way that a person performs activities. Other complexities that can be optionally addressed are to perform activity recognition in real time as the activities occur in a space filled with ambient sensors. In this case, data cleaning, segmentation, feature extraction, and mapping onto a label all need to occur almost instantaneously as the sensor events are observed. Yet another challenge is working with spaces in which there are multiple residents. Ambient sensors are not attached to individual people, rather they are embedded into the environment. This means that any number of individuals can be performing any number of activities at the same time. The challenge for activity recognition is to be able to recognize activities for multiple individuals in a single space from a common set of ambient sensors. This might involve steps such as tracking individuals through the space, separating one sequence of collected sensor data into multiple subsequences, one for each person, and attributing each subsequence to a separate person, and then performing activity recognition on those sequences. Another complex activity recognition challenge arises when we consider the fact that many of the ground truth labels that we use to train a machine learning algorithm are provided by the residents themselves or by an expert who is simply looking at the data and floor plan, or perhaps getting the labels from another automated system. As a result, any machine learning algorithm is going to be learning from potentially noisy ground truth labels. The machine learning algorithm that is trained from this erroneous labeled data is going to be learning to recognize the incorrect labels as well as those that are correctly labeled. In other cases, there may be no ground truth data for a particular person, activity, or environment. Ultimately, activity recognition should be able to perform well in new spaces where no ground truth is available, either by generalizing what has been learned in other environments with other people or through activity discovery. Once we tackle the activity recognition challenge, we then have the ability to describe behavior in terms of activity labels. Given those labels, we can correlate activity occurrences with parameters of interest, such as the person's health and changes in their health. We can also provide activity-aware services, such as automating the environment in ways that support an ongoing activity. In the next video, we will look at another way of analyzing ambient sensor data, specifically automatically discovering activity patterns from collected sensor data.